Hello again. So in this segment, I will allow myself to put my teacher mask on, and I like to introduce to those of you who are less familiar with quantitative methods and the quantitative lingo, what some terms mean, what ideas they they cover and they try to communicate. Um, I understand that some of you may find this already familiar, but nevertheless, I think this is relevant to discuss some of these issues here, okay? So let me start sharing my screen. Good. So this session is a brief introduction to some quantitative methods and statistical terms that may be useful when you're consuming and reading quantitative information and data from reports and papers. Once again, this is intended to provide you a first grasp on these terms if they are new to you. I understand that for some of you these terms may already be part of your common practice, of your everyday practice, but please bear with me during this segment. Let me clarify from the very beginning that this is not a course on introduction to statistics, introduction to quantitative methods, or a full course on numeracy. The idea here is, once again, to provide you a first understanding of these terms so you can make good use of them when dealing with numbers in your studies or practice. And if you find that my explanations of some or all of those terms has not been clear enough, let me know later and we can work on that. Okay. The first term I'd like to introduce is the idea of measurement. This is part of our everyday conversations. This is not an alien term to most of us. But there are some, not misunderstandings, but some less than ideal take on it, right? Usually, measurement is understood as attaching number to individuals or to expressed attitudes, to opinions, and so on, right? Even though this idea is not incorrect itself, it's usually perceived as having a negative connotation because it sounds as if we are just plugging numbers to humans and values and dreams and perceptions in a very cold way, right? But if we take a step back and rethink about measurement a little bit, we will find that measurement is just a different way or different form of categorization, right? And we do categorize entities very frequently. For instance, let's say that you go to a town and you interview 7 individuals for your qualitative project. If you find out and you report, for instance, that 5 of your interviewees were women and 2 of them were female, this is already a form of measurement, right? Because you are using certain socially constructed terms to differentiate these 2 groups of people. There are some of them that are in group A that I'm calling females, and others of them are in this other group, which I'm calling females, right? Males and females. So measurement is just a way to help our human brains to organize information, right? For instance, back to this example of males and females, in measurement lingo, this would be called nominal measurement, right? But we can also have other forms of attaching labels, names, or numbers or order to different phenomena that may be considered measurement as well. For instance, males and females or other genders is one form of nominal measurement. But you can also rank preferences. Say, out of these three different beverages, this is my top favorite, this is the second one, and this is the one I like the least. This is a form of measurement. If you are asked, for instance, to assign a number from 1 to 10 to a certain product, for instance, or to express your preference to a policy, this is a form of measurement. Because this last one use cardinal numbers, we tend to think of them as closer to what we understood as measurement, as the most recurrent idea of measurement. But as I mentioned, there are different ways to measure, right, using numbers or not, right? And there's different ways to measure phenomena. There's different forms, each one has its own imperfections and limitations, right? But once again, there's nothing so special about measurement. It's just, again, ways for us to organize our thoughts and organize information, okay? The second terminology I would like to discuss with you is what is usually referred to as observed and latent variables, right? These are two different ways of collecting information or to inferring information that are very simple, but there are some relevant differences between them. I think you will see that the definition of observed variable is more intuitive than the latent variable, but they are both very useful ways to organize and to gather information from phenomenon of interest. Okay, so let me start with observed variables. As the name says itself, an observed variable is simply a way to record information and characteristics that are or should be or could be directly observed. For instance, eye color. We can perceive, our senses can perceive that different individuals may have different eye colors, right? So this would be an observed sort of type of information, and this would be recorded in what we call observed variables, because again, our senses can perceive them, right? For instance, counting money is an observed variable. You have coins and notes that you can use to count, for instance, how much money you have in your pocket. Or you can use certain instruments to measure distances, heights, weights, and so on. Observed variables may look like they are universal in how they are measured, but that's not exactly the case, right? The categories and measures and the numbers and the symbols we assign to different observed variables will certainly vary depending on the context. For instance, simple things like measuring the weight of a pen, you can do it in pounds, kilos, stones, and many other different scales and ways to register that information. The same, for instance, for distance, right? We can use inches, meters, feet, and many other arms to measure distances. And even though most of these measures they may be converted into the other, they will not immediately sound familiar and meaningful to individuals from other contexts and with other cultures used to use different measures, right? But let me, for instance, now give you one example of a very simple way to, very simple example to use the idea of an observed variable. Distance, right? Distance is the space between two issues or 2 points, right, that we can measure using rulers, scales, in meters, in feet, etc. And the precision of this measurement will vary depending on the quality of and the precision of the instrument we use, right? But we can use certain instruments to measure distance more directly, right? Then we can measure other things. Another example of what could be an observed variable, but is a way more complex than measuring, for instance, distance or money in your pocket, is, for instance, the idea of race. even though the idea of race is associated to certain physical features and traits and physiognomical traits, skin color, hair type, and so on, that may be observable and they can be observed, the ways that we as humans will perceive this difference and record them are contentious and also again context limited, for instance, or bounded by the context and the categories in that context, right? In certain contexts, certain face traits may be more relevant, quote unquote, to be registered than others. For instance, in the United States, for many decades, a binary racial classification system was enforced. Whites would be only those with all their ancestry being European, right? And blacks would be classified as everyone who has some level of black ancestry or African ancestry, right? But in other contexts, this is not the case. In places like Brazil and South Africa, there are some intermediate categories to understand individuals of mixed background or who look different and so on. So not all observed variables are born equal, and some of them are way more complex to measure and to record than others, and the categories we use to understand what is relevant to be recorded will be context dependent, right? So yeah, not everything that is observed is simple to assign a label or number to it. We can talk more about this later, by the way. Second is the idea of latent variable. What makes observed variables different from latent variables is that latent variables cannot be directly observable, right? We do not see them, but we infer this variable from other information that we can measure or assess or feel somehow. One example is, for instance, depression. We cannot open someone's mind and look at their brain and say, well, this individual is experiencing depression, right? Well, some medical doctors would say that you can measure levels of certain hormones or neurotransmitters and so on, but you're still not measuring the depression itself, right? If there are different, say, there's a sort of chemical imbalance in your brain according to some studies, and that may make you depressed. This is not depression itself, right? We are inferring depression for a certain chemical process. Or for instance, we can observe that someone is in a low mood or is motivated or demotivated to do some things or have behaving in specific ways. Based on these things that we can somehow observe, we infer depression, but we cannot see depression directly, right? Another example could be, for instance, prejudice. We don't see the prejudice as prejudice in an individual. We understand that some individuals are more prejudiced than others because they behave in certain ways, they express some preferences and so on, right? So there is what makes latent variables so specific is that we are inferring what those variables are from things that you can see, but you cannot see the latent variables themselves. Let me give you an example here. Because latent variables are very relevant in social, political, policy sciences, but they are very difficult to assess for the reasons I just mentioned. We cannot observe them directly. So a proper analysis of latent variables will request very specific methodologies, and these methodologies may be quite complicated in some cases. But here's the idea of understanding what is a latent variable. So here we have this abstract dimension where there are so many things going on, but we cannot observe them directly, but we can infer it. When we see that certain individuals express certain opinions or act in different ways and so on, right? For instance, in the depression example, some individuals here may express they are they are in a constant low mood, they have behavior in certain ways that may indicate the motivation and so on. As you can see, these are very important to understand some social phenomena, but what these opinions and behaviors are just imperfect translations from this more abstract principle or dimension, right? We sometimes deal with so many, or discussing the social sciences with so many ideas or behaviors and phenomena or concepts, right, that we cannot observe directly, right? Concepts is a great example of that, right? We have an abstract idea of what something is, but we can only observe that indirectly in how it's manifested. And this brings us back to the previous conversation on race, is what is race and other social constructions? Are they better understood as, observed variables or as latent variables? This is an open, ongoing discussion, and I just like to flag this to you. There is no 100% consensus of what can be one thing and what can be the other one, right? Especially, some would argue that most issues we deal in the social sciences are latent variables because we are dealing with social constructions that do not have an existence in themselves, quote unquote, right? The next issue or next concept I'd like to discuss with you is the idea of sample, which is very intuitive and part of our everyday conversations. I would just like to give a more precise definition of it. A sample is a subset of a larger population or collection of objects, right? We use samples when we cannot gather information from all individuals or objects of interest. If you are going to study, say, the population of London, you hardly will have an opportunity to chat with all of the millions of people living in that town, right? So the use of samples is usually due to practical issues. We don't have the resources, the time, or the possibility of exhaust the collection of all important elements we would like to study, right? So instead of chatting with 7 million people, we can use a sample to understand in general, that a sample that approximates or not, depending on the sample you use, or a sample that resembles the broader population, right? And there are basically two different types of samples, right? We can break this in more details, but basically there are two larger blocks of samples. One is what is called a probabilistic sample, which is regarded as the gold standard in statistical analysis. Statistics and quantitative methods have a very consolidated technique to design and collect information and decide who will be part of a sample or not. These procedures and techniques are backed by robust centuries-old theory within a certain level, to collect information that will be representative of the broader population, right? And even though it's not a perfect resembles the larger population, there is not be a one-to-one correspondence in the findings we find in samples vis-a-vis the findings we would find if you had the chance of interview everything in a city or in a town. These procedures allow us to achieve some results with a very reliable level of confidence, right? Those results will be very reliable, right? Because this statistical theories behind them provide us tools to understand the margins of errors, the imprecisions, and so on surrounding the numbers we generate, right? So this is why they are the gold standards. This is the gold standard, right? When you see, for instance, in many cases, pre-election polls, we see that when we look at the actual results, the numbers are very close because the way this data is collected provides a more representative data of the the entire population or collection of issues, but probabilistic surveys are not as widely used as they should because the costs involved are very high. There's a second family of samples that is what I call here non-probabilistic samples. They are very handy, they are very easy to design, they can provide good insights, but they do not follow the same theory-derived procedures to decide who will be or not in that sample. So it's closer to what a convenience sample is, right? But because it's not backed by the same theories and procedures used in probabilistic samples, non-probabilistic samples may not be representative of the population, regardless of how large that sample is. But it's still, non-probabilistic samples may be very useful in many cases. For instance, you want to run a pilot study, or you want to you design a questionnaire, and you would like to know whether or not the respondents understand the questions properly, because maybe you may need to revise the wording in some questions or change the response options in other questions and so on. So non-probabilistic surveys may be very useful in many cases. And non-probabilistic samples have been largely used when we do, for example, qualitative studies, because sometimes what matters in quantitative studies is not how representative that information is, but some specificities and detailed information that you can gain from collecting that information from specific individuals, right? And also non-probabilistic samples is widely used in this so-called big data. Even though in big data, analysts may be handling millions of observations, they may have, say, information from millions of social media users. There is no guarantee that that huge amount of data is representative of the population, right? It's like, say, I interviewed 1 million individuals in London, but these 1 million individuals in London do not necessarily represent the entire England or the entire UK, right? So that's the idea behind non-probabilistic sample. It doesn't follow the same procedures to define who will be interviewed or not, and because of it lacks this theoretical background, there's no certainty about what or how representative that sample is. The next concept is the idea of distribution. This idea is very intuitive and useful, and it can be simply defined as a distribution is a representation of the occurrence of certain features in a pool of data. Okay? Usually we use graphic devices and plots to represent distributions just because it's going to be much easier to transmit of the idea of how the entire data, all the data we have, follow certain patterns or others. There are many ways to reduce distribution to numbers, or you can have like the distribution of all values in your data expressed in a table, but distribution is probably one of the best examples for that saying, one image is worth 1,000 words, right? Here, let me play, just to give an example of what is a distribution, let me play with you this example. Let's say that I stepped in a classroom and I collected and I asked the age of 15 undergraduate students. And this is, and these numbers here are the 15 responses I received, okay? We can, as I said, use a graph to demonstrate what, or to report what is the distribution of age among those 15 undergrads. And when you count each one of the ages and we see how many students have 17 years old, 18 years old, 19 years old, up to 24, This plot gives us a distribution of how many students reported each number as their age, right? We can see, if you count these numbers here, you will find that 5 students declare to be 18 years old, and this is the most common value in that group of students, and only one student reported to be 22, one to be 23, and one to be 24 years old, right? So following the idea of distribution, I'd like to briefly discuss the subtle difference between the ideas of probability and percentage. Probability is a more theoretical term in statistics and quantitative methods that tell us the likelihood of something to happen, right? And probability is theoretically defined in the range of from 0 to 1. 0 means the impossibility of an event to happen. 1 is the absolute certainty that an event will happen. So there is not much probability of chance here, but the numbers in between tell us what is the chance of the likelihood that something will happen. We can have, for instance, some things that will happen half of the time, right? Which, for instance, is sex at birth. It's more or less divided 50-50, right? A sister concept of probability is the idea of percentage. Percentage could be defined, I'm defining percentage here using my own words, is the share of the presence or occurrence of something out of a base of 100, right? And this usually expressed using from 0% to 100%, or its multiples, right? We can talk about sometimes 200% or 150% in salary increase and so on, or pollution increased by 75%. We use these terminologies in our everyday parlance. Even though probabilities and percentages are different, they may be used to express similar ideas, right? For instance, and the way we express our findings in probabilities and percentages is slightly different. For instance, in the example I just showed in the previous slides about the age of students, right? I interviewed 15 students, and 5 students out of those 15 told me they were 18 years old. If we express the prevalence of the share of students who are 18 years old out of those 15 students, we would find that 20% of the students interviewed reported to be 18 years old. In percentage terms, this is how we probably would express that idea, right? If we use a probability language, we would say there is a probability of 0.2 that a student is 18 years old. As we can see, the difference between, to convert a probability into a percentage, basically we multiply a number by 100, and to convert a percentage into probability, we just divide the number by 100. So there are some differences in what these different numbers mean in a more conceptual way, but they are easily translated from one to the other depending on how you prefer to express that idea. And a third way to express that 5 students out of 15 were 18 years old is to say 1 in 5 students was 18 years old, right? So these are just different ways to express similar ideas, okay? There is more, the idea of probability is probably more consequential when you go into in-depth study of statistics, where the idea of probability is more widespread than the idea of percentage. But as you can see, in terms of communication, the ideas is similar. Next, I would like to bring to the conversation 3 terms that are usually used to report data, right? And by these I mean the terms mean, median, and mode, right? These 3 terms are basically summary descriptions of a distribution, right? You take a huge bunch of data, and if you want to reduce that to describe it using one number, you would be using either a mode, a mean, or a median, right? So they are tools or ideas recurrently used to communicate findings. They may be very useful because they are simple, so therefore they are easy to communicate, but they can be extremely misleading, especially the mean. They can be extremely misleading if they are incorrectly interpreted or used out of context. And again, mean is the one that is most exposed to these risks here. Let me go back to our student example, right? For illustrate what the mean and median are. A mean, in its most common use, is the arithmetic mean. It's basically the average value in a range of values. For instance, in our example of the 15 students, we had all these numbers here as their age, right? So what do? We sum all those values and divide by the number of values. So we sum 18 plus 20 plus 19, etc., 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 to 24. And then because we have 15 different ages here, we divide the result by 15, right? And when you calculate the mean or the average age for those 15 undergrads, we find that the average age was 19.1 years. Right, so that was a summary of what would be the average age for those students. When we talk about the median is a slightly more complex idea, but once you understand it, it's very easy to see what's going on. The median is a value that distributes or that splits a distribution of values in two halves. You have half of numbers below the mean, half of the numbers above the mean. That's what it does. So to calculate or to know what is the mean of a distribution of values, you have first to order those numbers from the lowest to the highest, and then you find what's the mean. For instance, out of the 15 students we have, I order this bunch of numbers here, an ordered list of numbers here. I order them from the lowest 17 to the highest 24. And once I organize the numbers this way, I find that the mean value here is 19. So the median age for those 15 students is 19 years old. Okay. The last one is the idea of mode. Mode is simply the most frequent value in a distribution in a list of values, right? And it's important to keep in mind that a distribution of values can have more than one mode. For instance, if you have two numbers or values or categories that are equally frequent in a distribution, we may have two modes, like a camel or dromedary. I never know which is which, but if a distribution of values, imagine that the distribution of the age of our students, instead of doing this as it did like this would be this distribution would have two modes. So back to the simple example of our 15 students. The most frequent age reported out of these 15 different values was 18. It's the most frequent age. So the mode for those students is 18 years old. Got it? So let's move on. Let me now dive into two ways or two examples where the use of mean out of context or without giving it proper care to understand what that mean means, a pun not intended here. But well, the idea is to show you how the imprecise or less informed use of means can lead us to different results, right? That may not be very informative of the trend in the data we observe. As I mentioned earlier, means are very sensitive numbers. They can be very misleading depending on the context, and the most common context where means are misused is when there are extreme values in the data we have. Let me give you an example here. It is an example that I just made up. I have no idea what the real numbers here is, but let's imagine I live in a 4-flat building. And I'm curious to know what is the average income in the build I live in. And in these flats, I magically found that the income in each one of those flats are these numbers here. In flat 1, my neighbor makes 65,000 pounds a year. One of my other neighbors makes 48,000 a year. The other one makes 51,000 a year. The other one makes 57,000 a year. I'm not telling where I would be here, but let's say that combined the incomes in the 4 flats in my building are this one. One apartment makes 65k, the second apartment makes 48k, apologies. The third apartment makes 51k, and the last one makes 57k. If we sum these 4 numbers and we divide these 4 numbers and we divide them by 4, the average income or the average salary in my building is $250 pounds per year, 55,250 pounds per year, right? But now imagine that one of my neighbors move out, and then a former LSE president moves in. And full disclosure, the numbers I'm using here are either fictional or public information, so make your own judgment to guess which numbers are made up and which number is true and verifiable information out there. Okay, but let's say that one of my neighbors moved out and this former LSE president moved in. So now we have a change in the 4 observed and 4 registered incomes here. One person living in this building is making 65, the other is making 48k, the other is making 51k, and the fourth, my new neighbor, is making 539,000 pounds a year, right? So now that this person, this relatively well-off person, is moving in my building, is living in my building, then now the average income in my building is 175,750 pounds per year, right? So in this case, in the second case, the average is not as informative any longer, right? Because there's an extreme, very high value that is pulling the mean upwards, but the mean is not representative of the trend of these 3 other neighbors here, okay? Let me give you a 4th example, okay? For instance, another information that may be very sensitive is how means may, as I said, is very sensitive of extreme values and may not be a good representation of what the distribution is, okay? So for instance, sometimes governments brag that the national income is increasing, okay? For instance, in 2022, the average salary in the United Kingdom was approximately 35 pounds per year, okay? But how many Brits make the average, how many make above the average, how many of them make more than the average, right? And does the mean reflect the actual distribution of income in the country? Well, I collected data from official sources, and I plotted the distribution of the incomes here. Apologies for bringing this ugly graph, but this is just for information purposes here. And when we plot all the the incomes in a graph, the income for all individuals living in the UK, we see that the distribution of salaries in the UK is heavily tilted towards the lower end of income. And very few individuals make higher incomes here, say above £70,000 a year. These numbers are after taxes, just for your information. Okay, so let's try to understand a little bit more what this distribution is telling us and whether or not this average salary of 35K per year is a good reference or a good summary measure of the total distribution of wage in the UK. I organized the numbers I had from the lowest to the highest to calculate what is the median value in the UK. What is the median salary in the UK? And I found that the mean value is 35,000, but the median value is 24,500 pounds per year. Okay, so it shows us that because there are some individuals making so much money here, the average value it's about 10,000 pounds more than the median value. So let's recap what the median means. The median of 24,000 pounds and 500 basically means that half of workers in the UK make less than 24,000 a year and half make more than 24 pounds a year, right? The average is 35,000 pounds a year, and it's above the median because some very high numbers are pulling the average up, right? In this graph, there are other concepts called percentiles, which I'm not gonna go into detail here about them, but they are similar ways as they work similarly to the median, and they tell you how many individuals are below a certain value and how many individuals are above a certain value. When we look at the 75th percentile of the income distribution in the UK, this means that 75% of workers in the UK make less than that amount of money, and only 25% make more than that number, right? So the 75th percentile tells that 75% of workers in this case make less than a certain value. And that value is 36,000 pounds a year. That's the 75th percentile. Okay, so basically it means that even though the mean is 35,000 pounds a year, only 25% of Brits make 36,000 or more per year. So the mean here is not a good representation of the entire distribution because it's inflated by very high values. Okay, I understand that this may be a bit too much information for some of you who are being exposed to this for the first time, but I find it interesting to keep this general idea in mind. How the median is informative of how the wages are distributed in this country. We see that half of them make less than 24,500 pounds a year, and only 25% of the British make 36,000 pounds a year or more. So when you see the government talk, the average income in the UK increased, basically you may just have a few individuals or a few hundreds of individuals or a few thousands of individuals who are making an obscene a lot of money, and these very high salaries enjoyed by a very small part of the population is what explains the increase in the mean salaries, right? With this, I will finish my the segment, and I talk to you soon.